Hey, this is Jackson Ross. Today I'm talking about a paper called Binary Level Directed Fuzzing for Use After Free Vulnerabilities. Paper was published by Mandung Nguyen, Sebastian Barden, Richard Bonachan, Roland Graz, and Matthew Lemire. Okay, so the main problem this paper is trying to solve is that use after free bugs are both really dangerous and also are really hard to find reliably. A lot of fuzzers are good at finding crashes in general, but they're not especially good at finding this specific type of bug. The use after free usually depends on a very particular sequence of events happening in that order. So instead of just randomly mutating inputs and hoping for the best, or even just steering towards some target code location, UA-Fuzz tries to guide execution towards the actual pattern that creates the bug. That's a really big theme of the whole paper. You know, not all bugs look the same, so some buzzers should not treat them uh, as such. So I'm going to spend a little time on the background first. Just going to help explain the paper a little bit, tell you what UA-Fuzz is, how it differs, things of that nature. Okay, so why UAF bugs are so hard to fuzz? First, we should get into what a UAF is. It's a use after free bug, and it happens when a program allocates memory, later frees that memory, and then still tries to use it after it's already been, freed. So conceptually, it's something like, creating an object, destroying the object, and then accidentally keep treating it like it still exists. It's a bad situation because once memory has been freed, the program no longer owns it. So the memory could get reused for something else or overwritten, and oftentimes leaves you in an unexpected state. So if the program keeps reading it or writing to it, you can get crashes, corrupted data, unknown behavior, and even security risks in a lot of cases. This is not just a theoretical issue. A UAF, it's been one of the most important bug classes for security for a long time now, especially in bigger systems that dynamically manage memory. And the reason they're so hard to find is that you usually need more than one condition to line up for them to occur. It's not just like a reach one bad line and you find it. There's a lot of different variables to go into it, and even timings in some scenarios, which adds to the complexity. So fuzzing has to do with a lot more than just, hitting a location, basically. Why existing fuzzers struggle with this bug. The basic gray box fuzzer takes some seed inputs, mutates them, runs the program, and then uses execution feedback to decide which new inputs are interesting enough to keep. So usually it's based on like code coverage, or if an input reaches a new edge, new path, stuff of that nature, they get mutated more. Works really well for a lot of bugs because new coverage often correlates with exploring weird behavior, and weird behavior oftentimes triggers bugs. But the problem is that the coverage alone does not tell you whether you are recreating the right sequence, especially for these UAFs. So you might hit the allocation code in one execution and maybe hit the use site in a different. However, it doesn't necessarily mean that you're going to trigger the actual bug itself, because it needs to be in the right order, right relationship, correct events, everything matters. So directed fuzzers try to improve on this by guiding inputs towards specific target locations. So instead of rewarding any new path, they prioritize, paths that get closer to the code they care about, which is definitely better, but the paper argues it's still not enough. just because an input gets close to the use site doesn't necessarily mean that it's an actual bug producing sequence. So in other words, um, directed fuzzing can know where to go but still not understand what happens on the way there. So that's what the UAF is really trying to fill. It's the gap that's being closed. That's a little big picture stuff. At a very high level, UAF is still a directed gray box fuzzer. Still manipulates inputs, runs programs, all that good stuff. But what changes is how it measures what's a promising um, fuzzing output. So instead of asking, did this input get closer to the target code, UAFuzz asks, did this execution start to look more like a bug trace we care about? So that's the big question being asked here. The whole system is built around this idea of guiding executions towards an allocation, free, and use pattern. So that affects several parts of the design. It affects how target information is represented, how similarities are measured, how seeds are selected, everything from how mutation effort is distributed, how likely bug triggering inputs are filtered for expensive checking. So I think it helps to think of UA fuzz as a fuzzer with more informed sense of progress, essentially. So we'll get into a quick high-level implementation of a UA fuzz. So one important point is that this is a binary level tool. That means it works on compiled executables rather than needing source code. It matters because in real security settings, you don't always have the source, and when you do, source-based instrumentation can be heavier and oftentimes less practical. So at a high level, the workflow looks something like this. First, the system starts with a known or suspected UAF bug trace. And from that trace, it extracts the important program locations tied to allocation, which, allocations tied to freeing, and then later a use case, which causes these UAFs. So then it flattens all that into an ordered target sequence, and that's what the fuzzer eventually chases. During fuzzing, the binary is instrumented so that UA fuzz can observe its execution feedback, and it uses that feedback to estimate how um, a given run is close to the target trace. And a UAF, determined awareness of how close it is, I guess you could say, to that original bug. So yeah. So after that, based on the signals, the system decides which inputs are most promising, gives those seeds more fuzzing effort, and that way you're not wasting a lot of resources on, non-important seeds. Um, and we'll get a little bit more into how it decides that um, using a triage, which we'll get to shortly. So now that the implementation picture is kind of set in place, let's look at how we trace from bug trace to target trace. So the starting point for this is that for a known or suspected UAF dynamic bug reports, will often give you multiple stack traces. For example, they may tell you where the memory was located, where it was freed, and where it was used later on. Each of those events may involve, several stack frames. Now, that information in raw form is useful for humans, but not necessarily for the fuzzer directly. So the authors do in this paper is they transform, or as they call flatten the information into an ordered bug trace. That means the fuzzer gets a sequence of relevant target locations that represent the path towards the bug. Really smart design choice, because it turns like a messy debugging artifact into something that the fuzzer can actually use itself. It's exactly what a UAF needs to be debugged, because there needs to be context for the situation. So we'll talk a little bit about the three guidance signals that drive the search. And these are like three pretty basic things, but very intuitive. So one's target similarity, then we have UAF base distance, and cut edge coverage. The first one, target similarity, this is about asking how much of the desired trace the current execution matches, and whether it matches it in the correct order. That order part is really important. If an input hits some relevant code but not in the right sequence, it's a lot less likely and less useful to line up with the original bug. The second one, UAF based distance metric. Um, so normal directed fuzzings often use this. However, in the UA fuzz, it adapts the idea so that the measure is more meaningful for the bug class. It tries to basically reflect whether the execution is progressing through the right allocation, free and use stages. And then lastly, the cut edge coverage. It's about key branch decisions that help move the program towards the target trace. So it's not just any new coverage that matters, it's coverage that helps cross the important decision points on the way to the bug. Then we get into seed selection and energy assignment. So once UAFuzz can tell which seeds look more promising, it uses that info to basically devise its scheduling strategy. This is important because fuzzing is always dealing with a limited time and a very large search space. So there are way too many mutations to try them all. Fuzzer has to be kind of selective in this process. So it needs to decide which seeds are worth mutating and which are not really paying off. So UAF still cares about progress, but it defines progress in a more UAF specific way. So if a seed's execution matches more of the desired trace or follows the right order more closely, the seed gets more attention. So it's a lot more likely to stay in the queue. So the reason this matters is because for a hard bug like UAFs, there are often, partial executions that almost get there. Maybe one input successfully reaches the allocation phase, maybe one does freeing, but not later use case. There's a lot of different, scenarios where it's partially done, partially correct. So in a way, the scheduler becomes like part of the intelligence of the system itself. It's not just deciding what to mutate next. It's deciding, which incomplete bug stories are worth continuing. So that's pretty neat. Then we have bug triage. How are we going to avoid wasting heavy analysis? It might seem like a boring step, but this is actually really intuitive. Um, so finding candidate inputs is one thing, but confirming whether they actually trigger a UAF is another. Many of you know tools like Valgrind. I'm sure many of you have used that. Let's get a raise of hands in the back if you guys have used Valgrind. Okay. So a lot of us have. So tools like Valgrind can, help with the confirmation that it's memory safe, but they're very, very inefficient and expensive, um, especially over a large search base. So if you naively send every suspicious input to like a heavyweight checker like that, you're gonna waste a lot of time. So UA Fuzz handles this by using its own guidance information to filter candidates before deeper analysis. This basically says, out of all the generated inputs, which one actually looks like they have a serious chance of recreating the target trace. those are the ones worth checking. This improves efficiency a lot because it reduces the cost of post-processing and avoids, turning confirmations into the new bottleneck. And we'll get into some of the benchmarking. So basically they took a look at 13 real UAF bugs across 11 real programs. These aren't tiny programs, they're actually, designed systems. And a lot of these bugs are very hard to reach, so kind of makes it valid. So they also compared the UA fuzz against other directed fuzzers, which I believe is the right comparison because the claim of the paper is not that fuzzing suddenly became possible. It's just that this is, more effective for these UAF bugs in particular. So when I read this evaluation setup, the main question I keep in mind is, does building UAF specific guidance actually bias something like measurable or useful? And the paper argues yes, and we'll see why. So the main findings were that the UA fuzz generally finds the target bugs more often and finds them faster than the comparison tools, and that's important because some fuzzers might find things fast, and like have a very low success rate. So it's a lot of power being used, and then some are on the contrary, So having both means a lot in this scenario. Another thing I like about these results is that they are not just saying the tool got more coverage, because coverage could be weaker or more strong in certain scenarios or contexts. The real goal is bug exposure, and that's what they got in this results here. So they did find, that 34% were more successful runs on average, and about 2 times faster on average to expose bugs. So we can obviously tell that this works. A little bit about efficiency in real-world bug hunting. The paper also has 2 other results that make it kind of feel more complete. The first is efficiency, because the instrumentation is relatively lightweight, and because of the triage step, the overall workflow stays fairly practical, and that matters a lot in a large system, because it can get too expensive to use, and if it's too expensive to use, then it won't be used. Also, let's see. Oh yeah, the second is patch testing. This is part of another result the authors found, and uses traces from known use after free bugs, and it tests patched versions of the software. And if a patch claims to fix a bug, they look into it and see if fuzzing still finds executions that resemble the original bug pattern. So this actually found quite a large amount of bugs, so this was a good strategy as well that they found. We got some takeaways. I think the main takeaway from this paper is that it does succeed. That's the end all be all, and that a UAF is not just about reaching one dangerous function or crash site. It's about replicating the chain of events overall. So the UAF kind of builds that idea into the whole system. Changes how the target's represented, how progress is measured, how seeds are prioritized, how mutation efforts are assigned, and how candidate inputs are triaged. So